Hello there, welcome back to Differential Questions by Alexander. So today we're going to continue our discussion about the vibration of a mass on a spring. And the situation that we want to take care of today is going to be called the free undamped motion. And what that means is the following. You have a black coil spring, and on that coil spring you attach a mass to it. And so you have this gold mass attached to it. And so that means that the spring is going to stretch by a certain amount. That's my gray line that I drew. And so if you let go of it, then the spring is going to be bouncing up and down, up and down. And then what you want to do is you want to consider the original location, and then you want to know what is the function x that tells us the behavior of the spring as it goes up and down. And so that is what we're looking for. And then here we're going to assume that we have a free undamped motion. What that means is the following. Remember the last time we said that the full system takes care of the mass, takes care of the spring restoring force, the damping force, and then the external forces. And we said that using the Newton's law, then you come up with this formula. After you plug in everything, then you come up with this differential question. And what we're saying today is that we're going to make the beta is equal to 0. And so that is what we mean by undamped. So no damping, so undamped. And then the F is also going to be equal to 0. So that means that we have a free system, okay? So what that is in our list of equations is going to be the first equation. And so this is the differential question that we're going to look at. And now, since we actually have a physical situation, we are also going to introduce a little bit more terminology from physics to describe the behavior of the mass bouncing up and down on the spring. And again, ultimately, we want to know the formula for x. But once we know the formula, we also want to describe physically what else is happening, or what else can we say about the physical problem. All right, so now what we have is this equation. And then to simplify things, what we're going to do is we're going to divide by m everywhere. And so we write down x double prime plus k over mx is equal to 0. And what we're going to do is we're going to write this down as omega squared x. And what we're saying is this: omega squared is defined to be k divided by m. We're making this notation just to simplify the work later on. And so this is the equation that we're going to look at, but you just have to remember that we made the omega squared equal to the k divided by m, where k is the spring constant, m is the mass of that is being hung on the spring. So now one other thing that we also have to consider are the initial conditions. Remember that we have on the ceiling we have attached the black spring, coil spring, and then we put a mass to it, and then we know that this is going to stretch the original black spring to the gray spring that I drew here. And now what we're going to say is the following, just roughly speaking. We have an x-axis, and then we are going to say that is the original location, or the 0 location, and then the positive x-axis is going downwards, and then the negative x-axis is going up. And so what we want to do is we want to say we're going to stretch the mass a little bit more, furthermore. So stretch the mass that is attached to the spring, and so the spring is going to be stretched by even a further amount. And so what we're saying is that we are going to call that our x0 position, or our initial position at time equal to 0. But suppose that we also give it a little bit of kick to the gold mass. And so now we also are going to include an initial velocity. And so what that means is the following. We also are saying that the initial position of the gold mass is going to be at the location x0, and then the initial velocity of the gold mass is going to be v0, and that's going to be given to us in the problem. And so that means that our problem that we have is actually the following. So we have this differential question together with the initial conditions, and now we want to solve this differential question. This actually is an initial value problem. And so now the question is, how do you solve this? So this is the second order linear differential question, and it's actually a simple one. It is a homogeneous problem. And how do we solve this equation? So we assume that the solution is of the following format. We assume that the solution is an exponential. So I'm going to write it out as e to the at, and now our question is going to be, what is the number a? Previously, we wrote down e to the mt, but m in our physical situation refers to mass, so I don't want to mix the information. So I'm going to write down a. So we assume the solution is an exponential function. We plug it into the differential equation, and then we get the auxiliary equation. And for this problem, our auxiliary equation will become a squared plus omega squared is equal to 0. And remember that we know what the omega is. omega, just to recall, omega is equal to k, omega squared is equal to k divided by m. So don't forget that this is something we do know already. And so we solve for the a here in the auxiliary question, and then we get a is equal to plus or minus I omega after you do a little bit of algebra here. And so we get these imaginary numbers, but for our purposes, since we're dealing with a physical spring mass system, we don't want to work with the complex numbers, so we want to work with the real functions. And so instead of writing down x of t being an exponential function, we're going to say that our linearly independent solutions are going to be the trig functions, which are cosine of omega t. And then the second linearly independent function is going to be our sine of omega t. So those are our two linearly independent solutions. And so the general solution to the differential question is going to be the following. The general solution is going to be a combination of x1 and x2. So c1 cosine of omega t and plus c2 sine of omega t. So now notice that this is just using the differential equation. We haven't not used the initial conditions yet. So we got this to be our general solution to the spring mass system. So this is going to be the function that's going to describe our spring mass system. But at the moment, we do not know the C1 and the C2. And that's where the initial conditions come into play. And so with the initial conditions, we're going to figure out what the C1 and C2 are. And so using the first equation or the first initial condition, we are saying that if we plug in 0 into the formula, the output should be equal to the x naughts. And so we're going to do that. So C1 cosine of 0 plus C2 sine of 0, this will be equal to x naughts. And that is the initial position. But what do you know about the sine of 0? What is sine of 0? Sine of 0 is 0, so that entire term goes away. And what is cosine of 0? Cosine of 0 is 1. And so from this initial condition, we get that C1 is equal to x naughts. C1 is equal to the number x naughts. Now, in order to use the second piece of information that's given to us in the problem, we need to look at the derivative of the x function. And then so the derivative calculated to be the following. So this is going to be negative omega c1 sine of omega t, and then plus omega c2 cosine of omega t. All right, so now what does the initial condition tell us? The initial condition tells us that if we plug in 0 into this derivative function, the output will be equal to v0. So we are going to plug in 0 into this derivative that we just calculated. So negative omega c1 sine of 0 plus omega c2 cosine of 0. And then this is going to be made equal to v naughts. All right, so now again, the sine of 0 is equal to 0, so that first term goes away. And now cosine of 0 is equal to 1. And so that means that the information that we get from this step is the following. We get that the omega C2 is equal to V naught, or that C2 is equal to V naught divided by omega. So that is the value for the second constant. And now that means that we can update our formula. We had the general solution, but we did not know the C1 and C2. But now we have solved for the C1 and C2. And so now we can plug it in, and then we get our particular solution, our specific solution to the initial value problem, which turns out to be the following. So x of t is going to be c1, which is the number x naught, cosine of omega t, plus the c2, which is v naught divided by omega, sine of omega t. A little crowded there, but I'm saying that in words. So x naught cosine of omega t plus v naught divided by omega, sine of omega t. And that is our solution to the initial value problem. And now this is the function that tells us how the mass bounces up and down on the x-axis. And so we have solved the physical situation. We have solved the physical problem. We now know how the mass bounces up and down. So this is just a formula, but now since we do have a physical situation, we do want to say a little bit more than just write down the math formula. So we have a little bit more terminology. But before that, what I want to do is I want to repeat the story that I just said, but with the specific numbers. Instead of having the x naught and the v naught, I'm going to have specific numbers here. And so this is just a repeat of the previous question, but with numbers. And so let's look at the first question here. The first part, the first sentence, it says a mass weighing 2 pounds stretches the spring 6 inches. Okay? A mass weighing 2 pounds stretches the spring 6 inches. And so what that means is that we need to find if you were to read the whole problem, we need to find the mass, we need to find the spring constant before we can actually do anything with the problem. So the first sentence is saying that the mass weighs 2 pounds. Okay, and so what we have to remember is that weight is actually a force. So this is the force due to gravity, and so weight is equal to mass times gravity. And so the weight is 2 pounds, and then the mass is what we're looking for. And g is going to be, and since we're dealing with inches, which is feet, and seconds, this is going to be 32 feet per second. And so that means that the mass is equal to 1/16, and then this is going to be slugs. Okay, so that is the name of the units, and so that is the mass. Now let's go about finding the constant k. Okay, so remember that we want to write down our equation, which is mx double prime plus kx is equal to 0. So this is the equation that we are focused on. But in order to solve the problem, we need to know what the mass is, and we also need to know what the spring constant is. And so we got the mass, but now let's look for the spring constant. So again, from the first sentence, we said that the mass weighing 2 pounds stretches a spring 6 inches. Before we move on, we have to be very careful about our units. 6 inches is the same thing as 1/2 foot. Okay? So make sure that you put inches into feet, because those are the units that we're going to use. And so now for this part of the problem, we're going to use Hooke's law. And Hooke's law is going to say F is equal to Ks. Okay? F is equal to Ks. So this is the force that the mass does on the spring. This is the force that the mass does on the spring. And so there is no negative sign here. And so now the force is the 2 pounds that we said previously. And then we are looking for the constant K. And how much has the spring stretched? So it has stretched by an amount of 1/2 foot. And so that means that our K constant for the spring is equal to the number 4. All right, so now we can update our formula. And so our formula in red is going to be the following. This is going to be 1/16 x double prime plus 4x is equal to 0. Or in other words, we get that the x double prime, and then 4 times 16 is how much? 64. X is equal to 0. And so now we get this differential equation. Okay. So now, just looking at the differential equation, we can actually write down our general solution to the differential equation. And so we want to do that. And so here we either remember the formulas from before, or we redo the math that we have learned how to solve. And so here the omega is equal to, omega squared is equal to the 64. And so omega is equal to what? It's equal to 8. Okay. And now that you know the omega, and then you also know the general solution to the differential question, and you know that the general solution is going to be the following. So C1 cosine of 8t plus C2 sine of 8t. All right, so that is the general solution to the differential equation. So this is the general formula for how the behavior of the mass is going to follow. But at the moment, we do not know the C1 and the C2. Notice that we have done all this work just from the first sentence. Now we want to include the second sentence, and then from there we're going to get our initial conditions to figure out what the C1 and C2 are. And so that's what I want to do on the next slide. So we have our general solution, as we said before, and now we're going to use the information given to us in the second line to write down our initial conditions. So at time equal to 0, the mass is released from a point 8 inches below the equilibrium position. And so what that means is that our x0 is going to be equal to 8 inches, but 8 inches we have to translate it into feet. And so that means that that's going to be a 2/3 of a foot. Okay, 2/3 of a foot. So that is coming from the first piece of the sentence. So x0 is going to be 2/3 of a foot, 8 inches below, remembering that if we're to draw our x-axis, remember that we had the 0 location, and then going downwards is the positive x direction. And so what we're saying is that the release, this is going to be x is equal to 2/3. Okay, so 2/3. That's our original position where we let go of the mass. Okay. All right, so now what about the second part? Okay, so now we are also saying that there is a downward velocity of 3 feet per second. And so the V0 is equal to 3 feet per second. So let me just write down the 3 there. So that's good. So now with this information, we can do the same process that we did in the previous example, where we plug in the 0 and then we make it equal to the number, or we remember the formulas. So I'll not repeat the process. If you want to practice, you can practice plugging in the 0, make it equal to the 2/3, and at the end of the day, you'll get that C1. Remember that C1 is equal to your x0, and in this case, this is equal to your 2/3. And then C2, at the end of the day, is going to be equal to the V0 divided by the omega. And in this case, you get the V0 to be a 3, and then the omega was what? Omega was an 8. So now you can write down your solution to the differential question, which turns out to be the following. So 2/3 cosine of 8t plus 3/8 sine of 8t. So now this is the function that tells you the behavior of the mass as it moves up and down. So remember, the initial position of the mass is at 2/3 in the x-axis, and then we let it go, but there's a little bit of a velocity to it, and so it's going to be bouncing up and down. And so the way that it bounces up and down is given by this formula in the very bottom. And so we have solved the differential question, and then at the same time we have now given you a way to describe the behavior of the mass. And one other thing that I want to mention is this. I've been mentioning that this is the solution to the differential question, but in the physics terminology we say that this is the equation of free motion, okay, or the equation of motion. So they mean the same thing, except that we mathematically we say this is the solution to the differential question. Physics-wise, we say that this is the equation of motion. In this case, the equation of free motion, because there's no external forces. All right, so that's an example with numbers. And now again, since we do have a physical situation, we can say a little bit more about the physics here. And so let me introduce the following terminology. So we can also say something about the period of the free vibration. And so it's given by this formula. So T is equal to 2 pi divided by omega. And what that means physically means is this. If you look at your watch and you wait for a window of T seconds, if that is your unit of time, if you wait on a window for T seconds, then your mass will have made a complete cycle in that much time. Your mass will have completed a full cycle in that much time, which is 2 pi divided by omega. Mathematically, if you look at the graph of x, the graph repeats in that much time. That's what mathematically means. Now, the other type of information that we can get is the following. It's about frequency. And frequency, there's two ways to talk about it. One is mathematically. So graphically, it just means that there's that many cycles every 2 pi units. Or another way to talk about it in the physics notation, with the physics terminology, is that this means that the mass will undergo F complete vibrations per unit time. So if F is equal to 6, then this is telling you that there are 6 cycles per second. This is just an example. 6 cycles per second. All right, so that's period and that's frequency. And one other thing that we want to say about the system, that we can say about the system, is about the extreme displacement. And I have two different definitions here. They are talking about the same thing, but it's talking about the maximum displacement. In both cases, they are the same word here, but graphically they mean the max value of the x function and then also the mean value of the x function. So basically the highest that the mass will go and then the lowest that the mass will go. And both of them are called the maximum displacement, which means that the further away you are from the 0 location on your x-axis. So remember, you have an x-axis, you have 0, and what we're now saying is that the highest that the mass will go will be that yellow line, and then the lowest that mass will go will be the lower yellow line. But in each case, the yellow line away from the 0, that is the maximum displacement from the 0 location in both directions. All right, so now we are able to say or get the information about the period and the frequency from the formula that we just got for the x function. But now to talk about the displacement, we need to use a different formula, or we need to come up with the formula for the amplitude. And so now I'm going to introduce a little bit more mathematics. We introduced a little bit of physics terminology, but now we need to move a little bit to the mathematical side. And so the amplitude is going to be given by this formula. So it's simply given by the square root of C1 squared plus C2 squared. So that's pretty easy. You will have those numbers in your problem, in your formula, and so that's your amplitude. And now we also need to introduce this this angle phi, and phi is going to be called my phase angle. This is my phase angle, and this is going to be useful not for the problems that we have right now, but when we get to the circuits, we will talk about the phase angle a little bit more, a little bit further. All right, so now the thing that we want to also say is the following. We initially have this as our formula for our solution to the differential question, where we do know the C1 and C2, we have formulas for that. But what I want to say also is that we can also rewrite this formula. We're not going to change the formula, we're going to just rewrite the formula so that it looks different, so that it can give us a more clear picture of what's going on physically. And so with the information that I wrote down on the top, I'm going to do the following. So I'm going to divide by A. Okay, so I'm going to divide by A the C1 and the C2. But just remember, I don't want to change the formula, but in order to counteract the dividing by A, I'm going to multiply by A. Okay, I'm going to multiply by A. So I haven't changed the formula. So that's the tricky part. I have not changed the formula. And by doing that, I can say the following. So I'm going to factor out the A, and if I factor out the A, I get C1 divided by A cosine of omega t plus C2 divided by A times the sine of omega t. Oops, I put a square bracket there. And now what do we know about the first fraction, the C1 divided by A? We define this to be the cosine of the angle phi. We made this definition on the very top, and so we're going to replace that fraction C1 over A with the cosine phi. And so if I were to write this down again, so I'm going to write down A square bracket, and I'm going to write down cosine of phi. So my pen is delaying a little bit. There we go. So cosine of phi, cosine of omega t, and then the second parenthesis, which is the C2 divided by A, that's going to be replaced by a sine of phi, and then we have sine of omega t. And now here is going to be a little bit of a trig identity that we're going to use. So cosine of x minus y. So this is going to be a trig identity that we're going to use. And cosine of the difference of two things is going to be cosine of the first one, cosine of the second one, plus sine of the first one, sine of the second one. So there's a plus here in between. And so what we're going to do is we actually have this right side of the equation of the identity, and then we're going to write down the left side. So that's how we're going to use the identity. And so we are going to write down the following. We're going to write down x of t is equal to a cosine of phi minus omega t. Okay. Cosine of phi minus omega t. And now one last thing that I want to do here before we move on, I'm going to rewrite the inside. Since we have a minus sign here, and since cosine is an even function, I'm actually going to write down x of t is equal to a cosine of omega t minus the phi. That is usually the format that we want to put it into. So what we have done is this. The original formula that we had, which is in the black box, we did a little bit of trig identity here. We did a little bit of manipulation, algebraic manipulation, and then we are going to rewrite this formula in black. We're going to rewrite it into the blue formula on the very top. And now with this formula, we like this formula because it actually gives us the amplitude of the oscillation. It gives us the angular frequency, and it also gives us the phase angle. Okay, so it gives us a lot of information about the physics related to the physical problem. All right, so just remember the formulas that I have on the very top. And remember that you can do this translation. You can translate the original black box function into the blue box function on the top. And we haven't changed the formula, we just changed how it looks. They are actually the same formula, but they just look a little bit different. All right, so now just a little quick exercise here. If the equation of motion is given by this x function, then we want to determine the period, the amplitude, and the phase angle. So the period we can calculate just by looking at the formula. here we have to remember that the period is given by what formula? Is it 2 pi over omega, or is it omega over 2 pi? It's going to be 2 pi over omega. So that means that we have to identify the omega. But before we move on, you have to remember that omega squared is equal to k divided by m. I just want you to remember that part because it actually physically is important. But now for our problem, we already have the omega, which is number 7 in this case. Okay, and so the period in this case turns out to be 2 pi divided by 7. Okay, and then this is roughly approximately how much? So pi is approximately 3. So that's 2 times 3, which is 6. So this gives you 6 over 7 seconds. So this is a very rough approximation, and we're saying that the period is 6 over 7 seconds. So not even a full second, and then there is going to be a full oscillation to the system. That's what the period tells us. A full oscillation occurs in almost 1 second. All right, so now let's talk about the amplitude. How do we calculate the amplitude? So we have a formula for the amplitude. The amplitude is given by the formula c1 squared plus c2 squared. And here we know what the c1 and the c2 are. And so in this problem, we just plug in the numbers. So we get 9 plus 16, which gives you square root of 25, which gives you the number 5. So the amplitude is 5. And then what that tells us is that the mass, according to our vertical x-axis, where here's the origin, the mass, the highest that it will go will be -5, and then the lowest that it will go will be +5 in the x-axis. So the mass is bouncing up and down. On the vertical axis, and the highest that it will go will be -5 in the x-axis and +5 in the x-axis. And then not only that, we also know that the time that it takes to make a full cycle is 6 over 7 seconds, which is roughly very, very close to 1 second. All right, so now the other thing that we want to calculate is the phase angle. Okay, the phase angle is going to be a little bit tricky, and so I'm going to do that a little bit careful here. So the way that I talk about it is the following. I draw my C1 axis and my C2 axis. And now I'm going to, since my numbers are 3 and 4 for C1 and C2, I'm going to draw a line here. And that is going to be, the ending point of that line is going to be a 3 and a 4 on my C1 axis and C2 axis. And so what we are getting is the following. Okay, I'm going to focus on this triangle that I'm going to put in gray now. Okay, so this triangle in gray, and then this is a right triangle. And then the angle, the phase angle, is actually the angle from the positive C axis to the black hypotenuse. The phase angle is from the positive C1 axis to the black hypotenuse that I drew. So now, if you go back to your formulas, and actually you could go back to the formulas, but you can actually just label the information that you have here. And the vertical leg is magnitude of 4. And then the bottom of the triangle has a length of 3. Okay. So ignore the black parts, the black labels that I put in there. That it will be important for the next example. But now let's just focus on the gray triangle. The base of the triangle is 3. The height of the triangle is 4. And now what we want to find is the phase angle. But we're going to look at the tangent of phi because we know the opposite and the adjacent to this. And so opposite is 4, adjacent is 3. And so that means that the phase angle is going to be tangent inverse of 4 over 3. Okay, tangent inverse of 4 over 3. That is your phase angle. Okay, but now this is, if you put this into the calculator, you will see that this would be close to the angle pi over 3. Okay, okay, this is close to the angle pi over 3 if you put it into the calculator. So, but the actual answer is what we care about, which is this thing here. Okay, so this is the actual answer, and we're saying that this is approximately pi over 3. All right, so that's the phase angle for this problem. Okay, but now it gets a little bit tricky if we were to change the numbers, the 3 and the 4, just slightly. Okay, so we are done with this problem, and I'm going to rewrite the problem where I'm changing the 3 that we have on our x formula, and I'm going to change that into a -3. Okay, so the period will still be the same as before. So the t is the same as before, and remember that the formula is 2 pi over omega, and so this becomes 2 pi over 7, we said that this is approximately equal to 6/7 seconds. So the period stays the same. And now the amplitude, it stays the same because of the formula. You square the number, so this gives you 9 plus 16. And so at the end of the day, you still get this amplitude to be 5. Okay. So the amplitude still stays the same. But now when it comes to the phase angle, we do have to be careful. And then this is why I draw my C1 axis and my C2 axis. And now, according to the numbers that I have, I'm going to draw a line in this direction. And because that point is the point -3 and then +4 on the C2 direction. And now the angle, the phase angle that we care about, that we are looking for, is actually the angle between the C1 axis and the hypotenuse of the triangle that I will have drawn. So the phase angle is actually from the positive C1 axis and the black line that I drew. But now what I'm going to do is I'm going to focus on the triangle that I'm putting in gray now. Okay, so focus on this triangle that I'm putting in gray, and this is a right triangle. And now ignore the -3 and then the +4, and I just put in the length of the triangle. So the height of the triangle is 4, the base of the triangle is 3. So you forget about the C1 and C2 axis, and right now you're focusing on the gray triangle. And now we want to find the angle phi, but what I'm going to do is I'm going to find the angle, what I'm going to call psi. So this is the Greek letter psi, which looks like a fork. It looks like a fork. That's my Greek letter psi. And so I'm going to use the same formula that I got from before, the tangent of psi. We know that that's going to be opposite over adjacent, which in this case is a 4/3. And now that means that the psi angle is going to be tangent inverse to the 4/3. And we said that this is approximately equal to pi/3. All right, so what we're saying is this: we don't care about the psi angle, we care about the phase angle. And according to our picture, to get the phase angle, this is going to be equal to pi minus this psi angle. And so according to our information, this should be pi minus the tangent inverse of 4/3. Okay, so that is our phase angle. And if you want to approximate this, this is going to be equal to pi minus pi/3, which gives us a 2pi/3. Okay, so the approximation of this phase angle is 2pi/3. But I want to make sure that we understand that when we calculate the phase angle, we do have to be careful. And so I do draw my C1 and C2 axis, and we have 4 cases, but instead of memorizing 4 cases, I just draw my C1, C2 axis, put my triangle, and then I need to make sure that I understand that my phase angle is from the positive C1 axis, down to the hypotenuse of my triangle that I draw. All right, so that's just a little bit of this discussion about the phase angle, that it will be very useful whenever we talk about circuit theory. All right, so now I want to give you a little bit more discussion problems where we are going to use the formulas that we just introduced. All right, so suppose that we have the equation of motion to be this formula, this x of t formula. And now this is in the new format. And then we want to know how many complete vibrations the mass will have completed at the end of 4 pi seconds. Okay, how many complete vibrations will the mass have completed at the end of 4 pi seconds? And 4 pi seconds is approximately how much? So pi is approximately 3, and so this is approximately 12 seconds. So you have a mass bouncing up and down, and then you want to know in 12 seconds how many oscillations will that mass have completed. And so you need to know the frequency here. And then how do you calculate the frequency? So frequency is omega divided by 2 pi. Frequency is omega divided by 2 pi. And again, you need to know what the parameters are here. So the omega in the problem is equal to 4. Okay, in the formula, the omega is equal to 4. And I'll just remind you again, omega squared is equal to k divided by m. We're not using this, but I want to kind of remind you that this is what the physical parameters give you for the omega. All right, so now going back to the frequency problem. So this is going to be equal to 4 divided by 2 pi. And so this is going to be what? 2 over pi. 2 over pi, which is roughly 2 over 3. All right, so that is the frequency for this for this problem. So 2/3 cycles per second. That's what this is telling us. 2/3. So 2/3 cycles per second. That's what the frequency is. But now we want to know, if we wait for 12 seconds, how many cycles will have been completed. And so all we have to do is we need to multiply the frequency multiplied by the time that we are waiting. And so in this case, it's going to be 2 over pi multiplied by the 4 pi. That's the time that was given to us. And so the pi goes away, and then it's going to be the number 8. And so what this means is that there are going to be 8 cycles that the mass will have completed in that much time. So 8 complete cycles will be completed. All right, so that's one type of problem. Now let me say a different type of problem. Suppose that we have the following formula for our equation of motion, and then the question is asking us, determine the time that the mass attains its displacement below the equilibrium position, numerically equal to half the amplitude. So again, we have the vertical x-axis, we have the original location to be labeled 0, and then we have a specific amplitude to the problem. So this is the highest that it will go, and then the lowest that it will go will be positive a. So that's the mass will be bouncing between those two numbers, the negative a and the positive a. And then what we want to know is, if we are looking at half of the amplitude, and then the amplitude in this case is what? 9/2. A is equal to 9/2. What we're saying is this: the mass will be bouncing up and down, and we want to know at what specific time will the mass be crossing that specific location. At what time would the mass be crossing that specific location, which is half the amplitude? And so what we're going to do is we're going to set up the problem in the following way. We want to know at what time the position of the x will be equal to half of the amplitude, which is, in this case, is half of the 9/2. And yes, I can simplify this if I wanted to. This is 9/4. But instead of doing that, what I'm going to do is this. I'm going to write down my formula for x, which in this case is going to be 9/2 cosine of this entire thing, 3t minus 13 pi over 7 is equal to 1/2 of 9/2. So now I wrote it out this way because now I can cancel out the 9/2 from both sides. And so now I have my cosine of this thing in the parentheses is equal to 1/2. And so now the question still is, for what time will the cosine of this thing will be equal to 1/2? And so let me rewrite this slightly. And so this is going to be written as the following. So instead of writing down 3t minus 13 pi over 7, I'm just going to write down theta. So just to make it a little bit easier to understand what's going on, we're asking, for what angle is the cosine of that angle equal to 1/2? For what angle is the cosine of theta equal to 1/2? And so the angle will be what? So let's think about it. Cosine of what angle gives us 1/2? Is it pi over 6, pi over 4, or pi over 3? Well, it would be pi over 3. Okay. So pi over 3. Is that the only angle that gives us cosine of pi? Cosine of pi over 3 does gives us 1/2, but is that the only angle? Are there any other angles? Yes, there are. There's infinitely many. So if we go around the circle, what would the next one be? It would be 5 pi over, not 5 pi, it would be oh yeah, 5 pi over 3. I was thinking something differently. So 6 pi over 3, that's a full cycle. Okay, so that'll be 2 pi, so we're not quite there. And so this continues on forever. Okay, so you can continue on the list. You should probably write down a few more, but let me just give you the first two. So this is the angle where the cosine of that angle is equal to 1/2. But now we replace the theta with this theta, with this 3t minus 13 pi over 7. And so what we're going to do is the following. We're going to write down the following. We're going to write down 3t minus 13 pi over 7 is equal to pi over 3, comma, 5 pi over 3. And then we have a list of numbers here. And now our task is to look at this blue box at the very bottom, and then you solve for t. Okay? You solve for t, and that's how you get your different times. So 3t minus 13 pi is equal to pi over 3. That's the first equation that you have to solve for t, and then you will get the value for t. And that's the first time where your mass is going to be at the location half the amplitude. Then you have to set the, let me put this in purple, then you have to set this 3t minus 13 pi over 7, you have to set it equal to 5 pi over 3. Then you solve for t, and then that will give you the second time where the amplitude is, where the location of the mass is, again, half the amplitude. All right, so that's all I want to say about this. I want you to think about this last problem, but we want to emphasize that with this format of the equation, we can actually get a little bit more information about the solution. Okay? We had our formula for x of t in terms of cosine and sine, but if we put into this format, we know what the amplitude is, and we also know what the phase angle is. I haven't asked any questions about the phase angle here, but it will become useful whenever we deal with circuit theory. So I hope that this discussion is hopeful. I hope that breaking down the problem into parts, it makes it more manageable. And on the next video, we're going to be dealing with the situation where we include damping to the spring mass system. Today we deal with the free undamped motion. Next time will be free damped motion. All right, so thank you for joining. Thank you for tuning in, and I'll see you next time.